Welcome to The Explainer. Today, we're going to decode the feed-in logic that powers, well, almost everything, from your coffee machine to the bad guys in your favorite video games. It's called a finite-state machine, and by the end of this, you'll see how this really simple idea is one of the absolute cornerstones of our digital world. All right, let's dive in. So instead of starting with a dry, boring definition, we're going to kick things off with a puzzle, one that seems kind of impossible at first glance. I mean, just imagine a machine that's so simple, it can only remember one of two things at any time. It's basically a light switch. It can be on or it can be off, and that's it. So how could a machine like that possibly compute anything useful? Well, here it is. This simple little diagram is our puzzle solver. And you can see it only has two states, or two memory slots, that we're calling S and T. That is its entire world. Its memory is just knowing which of these two circles it's currently sitting in. So, what's the specific challenge we're giving our little machine? It's this. We want it to read a string of ones and zeros, one digit at a time, and tell us if the total number of ones is odd. If it is, the machine should accept the string. And if not, it should reject it. Okay, so how on earth does it actually work? This is the fun part. Let's trace an input string and actually watch this machine think. We're going to feed our machine the string 110. Now, we can see it has two ones, right? That's an even number. So the machine should reject it. Let's see if it can figure that out. Let's imagine a little gnome is our processor, and he starts his journey at state S. How do we know it's the start? Well, see that little arrow coming in from nowhere? That's the start here sign. Okay, the first character is a 1. Our gnome looks at the rolls from state S, sees the arrow labeled 1, and just follows the path. So he moves from state S right over to state T. Simple as that. Next up, the second 1. Well, our gnome is now in state T. He looks at the rule for reading a 1 from here, and that arrow points right back to state S. So back he goes. And finally, he reads the 0. From state S, the transition for a 0 is just a loop that points right back to itself. So our gnome doesn't go anywhere. He just stays put. And that's it. We've reached the end of the string, and our gnome has ended up in state S. Now, look closely at state T. See that double circle? That's a special marker. It means it's an accepting state. Since our gnome ended in S, which is not an accepting state, the machine rejects the string 110. It got it right. Pretty brilliant for such a simple device. So, here's the crucial idea. Those circles, they're called states, and they represent the machine's entire memory. In this case, state S is basically the machine's little note to self saying, so far I've seen an even number of ones. And state T is its note to self saying, so far I've seen an odd number of ones. And the arrows? Those are the transitions. They are the simple, pre-programmed rulebook that tells the machine how its memory, its state, should change when it sees a new piece of information. The entire logic of the machine is right there in those arrows. So this little puzzle solver we've been playing with is a perfect example of a really powerful concept in computer science. So let's zoom out a bit, look at the formal blueprint, and see how this builds into something even bigger. What we've been looking at is formally called a deterministic finite automaton, or DFA for short. It's really just a mathematical model for any machine that has a limited or finite number of states it can be in. And it turns out every single DFA, no matter how complicated it looks, is built from these same 5 ingredients. You've got to have a set of states. Those are our circles. You need an alphabet it can read. For us, that was just zeros and ones. You need one and only one start state. You need a set of accepting states, the double circles. And finally, you need the transition function. That's the rulebook, the arrows, that tells you exactly where to go next. And this is where it gets really cool, because these principles can scale up to solve way more complex problems. I mean, look at this thing. It might look a little crazy, but its job is actually pretty straightforward. It tells you if a binary number is divisible by 5. How? Well, it has 5 states, one for each possible remainder you can get when you divide by 5. 0, 1, 2, 3, or 4. If our little gnome ends its journey in the state labeled 0, it means the number has a remainder of 0 and is a perfect multiple of 5. And this table here, this shows you how a computer would actually see that diagram we were just looking at. It's just a simple lookup table. For any given state you're in and any input you read, there is exactly one place to go next. No ambiguity. That's the deterministic part of the name. Now you might be thinking, okay, this is some neat abstract theory, but I promise you, you interact with these machines constantly, every single day. You know, this core idea, of moving between defined states based on some kind of input, it's not just for computers. It's a fundamental pattern for how systems change. Even Emerson got it. The real action, the power, is in that moment of transition, the move from what was to what comes next. Seriously, just think about it. A simple analog clock is a finite state machine. It has 720 states, one for each minute in a 12-hour cycle. A Rubik's Cube? Every single turn is a transition from one state to another. They both operate on the exact same principle, a limited number of possible configurations with clear, defined rules for moving between them. And that number on your screen? Yeah, that's how many possible states or configurations a standard 3x3 Rubik's Cube has. It is a mind-bogglingly huge number. But, and this is the important part, it is finite. But that key word finite is everything. As powerful as these machines are, that limited memory creates a hard, unbreakable wall on what they're able to compute. So, what's the deal? Well, on the one hand, they are amazing at pattern matching. They can easily check if an email address is formatted correctly because those rules are finite and predictable. But on the other hand, you hit a wall. Ask one of these machines to do something that requires unlimited counting, like checking if a string of any length has an equal number of zeros and ones, and it just can't do it. To keep a running count that could go on forever, it would need an infinite number of states, and that breaks the fundamental finite rule. And this limitation, it actually reveals a really profound idea in computer science. Computation isn't just about having clever rules. It's fundamentally about memory. The more stuff you can remember, the more complex the problems you can solve. Which leaves us with a final thought to chew on. If this is what a machine with finite memory can do, what could a machine with infinite memory accomplish? But that is a question for another explainer. Thanks for watching.